Hi guys, Buildzoid here, and today we're going to be taking a look at the core voltage regulation of the ASUS Maximus Z790 Apex. The board was provided by ASUS, so big thank you to them for sending it over for testing. And with that out of the way, let's get into it. Now, in terms of the setup here, I'm running a 13900K with a slight underclock, just because for, like, if we're taking measurements, we don't want the CPU to crash, because that's not particularly conducive to taking good measurements when the CPU randomly shuts down. So yeah, the CPU is slightly underclocked, and we're going to be going from LLC level 8 all the way down to level 4, because below level 4 there is so much V-droop that we'd have to be idling at like 1.6 volts to get a reasonable load voltage, which, yeah, I'm not doing that. Not on air cooling. Or, well, it's not air cooling, it's on an AIO, but I like ambient cooling. Anyway, yeah, so static voltage control, and also the ring is at 4.6, which isn't particularly high. And yeah, and then I have like a basic memory XMP profile enabled, but that's not relevant because the workload we're running doesn't use the memory, because yeah, we don't actually want that for this kind of testing. Anyway, so yeah, that's the first setup that we're going to be running. I'm just going to save and reset at this point, and while we wait for this to boot, we're going to go over the rest of the test setup. So the oscilloscope is connected to the back of the CPU socket with some coax, and there's a 50 ohm termination at the oscilloscope. The oscilloscope that I'm using is a Rigol HDO 1104. Big thank you to my supporters for making it possible for me to purchase this scope. Patreon stuff down in the description. Anyway, yeah, so that's how the oscilloscope is connected to the motherboard. There is one major downside to the way that I've decided to connect the oscilloscope to the board, which is that if you're measuring from the back of the CPU socket, you obviously aren't, like, you have the impedance of the CPU socket between the, the actual chip and where the oscilloscope is measuring. So compared to the CPU, we see significantly higher average voltages than what the CPU does, because the CPU socket has, relatively speaking, a lot of resistance. You can easily have like a 70 millivolt voltage drop across the CPU socket. Also, some of that voltage drop is from the CPU substrate itself, but a good chunk of it is just the socket itself. Like, LGA sockets are not particularly great for power delivery, which is why you don't see GPUs using them. And the other issue is the socket also has some like inductance to it, and in theory we should be seeing somewhat less undershoot on the back of the board, because the undershoot sort of, if you like, you can sort of think about it as starting from the CPU, whereas we should be seeing maybe more overshoot, because that starts from the VRM. So basically, not the, like, we're not, what the oscilloscope is seeing is not exactly the same as what the CPU is seeing. We're seeing somewhat less undershoot, somewhat more overshoot, and the average voltage is way above what the CPU is actually getting. And the other concern is this method isn't ideal for comparing different motherboards against each other, because depending on how their power delivery network is designed, the impedance to, the back of the CPU socket is not going to be the same. So, yeah. Anyway, that's how this is hooked up, and now let's actually throw some load on this and talk about how this measurement works. So the workload that I'm running here is Y-Cruncher small FFTs, and it's set to use 50 megabytes of memory. So it basically runs in the L3 cache, which is why we don't have to worry about the memory settings, which is why I'm just running like a 6200 XMP. Now, anyway, if we just run the workload like this, we see that our average voltage is, quite high at 1.317 volts, considering that we have 1.24 volts set. And that's because there's like an 80 millivolt voltage drop across the CPU socket. That's literally why that happens, is the CPU sockets are very high resistance. Anyway, the idea behind these measurements and what we're looking for is the motherboard good or bad? or more like, is the LLC setting good or bad? Well, admittedly, sometimes you get motherboards where it's impossible to set the LLC low enough that you get no undershoot, but this is not one of those boards. So basically what we're looking for is we want this minimum voltage over here to be as close to the average voltage as possible. And yeah, right now we're already seeing like a 60 millivolt difference, right? If I reset the statistics again, yeah, we get like 1.32 volts average. You can also notice that the average voltage is drifting up over time, and this is as the power plane heats up and the CPU socket heats up, so there's just sort of more resistance in everything. Because, yeah, that just happens with metals. As they heat up, they tend to get more high, like the resistance tends to increase. Anyway, so yeah, we have something like 60 millivolts of undershoot here because we're going from like 1.32-ish volts down to 1.26, which is not great. Also, why we're getting these periodic spikes is just the Windows event timer. It's just how Windows like makes sure that everything is running. We can make this worse if we just move the mouse around because processing user input is somewhat more difficult than just checking that everything is still running. And now we see undershoot all the way down into the 1.218 volt range, which is bad because that is like less voltage than we get at idle, right? At idle, if I stop the workload, we get around 1.24 volts. So yeah, this is like really like this is just straight up undershoot. It's kind of impressive with the Apex though. Even when we're running this like awful load line calibration setting that we're running right now, is that we just let the board sit like this. The peak to peak is actually quite low. Yeah, which not particularly useful as a measurement because ultimately when your CPU blue screens when running a workload, it's because of the undershoot, not because of the overshoot. So the overshoot, yes, it looks very ugly, but it's actually not a concern. Yeah, like low peak to peak values always look impressive even if they don't necessarily mean that much. Pretty much anything under 200 millivolts can be considered generally good. As in, you can have a board that has like 200 millivolts peak to peak, but you can set it up so that you don't have any actual undershoot when running load. Anyway, so that's level 8 LLC. Nothing particularly impressive. We get undershoot down into the like 1.218 volt range, and the average voltage is above 1.32. So around what, like 110-ish millivolts of undershoot. Anyway, what's kind of neat with the Apex, well, there's a lot of neat things about this board, but one thing I do like about the LLC settings here is that level 8 and level 7 are actually significantly different. There's a lot of motherboards out there where the last two LLC settings are basically the same, where the very last one is no V-droop, and the second last one is like almost no V-droop, which is not useful. There's like not having any V-droop has its uses. It's perfect for like thermal testing because you don't want the voltage to go up and down based on the temperature of the CPU. That would be really inconvenient. It's not particularly helpful. Like that's inconsistent. But yeah, having having an LLC setting where you get like 20 millivolts of V-droop at like 200 amps output current, not useful because the voltage regulation still sucks, and now you also don't have the consistency of like no V-droop LLC. So anyway, level 7. Also, the Apex does offer a bunch of other VRM settings, like VRM, yeah, like settings. In my testing, I haven't found any of them to actually make any difference. So like raising the switching frequency or lowering the switching frequency doesn't really do anything, at least within my measurement capabilities here. It's possible that maybe if I was hooked up directly to the CPU, it might actually pick up, but on the back of the socket, there is no difference between 300 kilohertz and 800 kilohertz in terms of voltage regulation. And so, yeah, there's really no reason to not just leave that on auto, in my opinion. I do have the VRM spread spectrum disabled, though I haven't checked if that actually makes a difference either, so that might not be necessary, but yeah, anyway. And then you have like the power duty control, which that doesn't seem to do anything in my testing, so yeah, could be a limitation of my measurement methodology here, but I'm leaning towards, like, it's not uncommon in my experience for motherboards to have a bunch of, like, VRM configuration options that don't do anything. This wouldn't be the first time I've run into that. Especially on high-end boards. Like, low-end boards, there you might find that, like, changing the switching frequency actually helps, or at least does something, but a lot of high-end boards are just so good on stock settings that there's really no room for improvement. So, anyway, we're going to go to level 7. Also, it's just ASUS that gives you this many VRM setting options. Like, most boards... Actually, a lot of boards these days won't even necessarily give you a switching frequency option, which I really don't think is a problem. Because, again, like I mentioned, even when you do have the option to change it, like, say, you do on this board, changing it doesn't tend to do anything. So, not having it, in my opinion, isn't really a problem. Yeah, it's like, and that's probably actually one of the reasons why, like, these days there's a lot of boards that just don't let you change the switching frequency, because, yeah, it a lot of the time, it just doesn't make a difference, so you may as well leave it on the auto value. Anyway, let's hit Y Cruncher again. Apparently I didn't wait for Windows to settle down. There we go. So now we're seeing, if I don't move the mouse, we have the same average voltage, right? We're right up again at like 1.318-ish volts. Previously, we were at around 1.32. The voltage is climbing up again because of thermal effects. Anyway, now we're seeing significantly less undershoot, at least if I don't touch the mouse, right? Because we're getting like 1.29 volts versus 1.32. Previously, we would be getting about 1.26. So yeah, level 7 LLC is already a significant improvement in terms of voltage regulation compared to level 8. But there's really not much reason to use it, and if you do start moving the mouse around, things aren't looking so great again. Though what's kind of fun is if I don't move the mouse, our peak to peak is even lower than before. It's down to 70 millivolts, which honestly, this is like the kind of voltage regulation I expect on, say, like a GPU's memory power delivery. Seeing this on a like CPU Vcore VRM is yeah, that's impressive. Now, admittedly, that's only the case if I don't touch the mouse, because as soon as we have that like transition from processing mouse input to running Y Cruncher, yeah, it doesn't do so great anymore. But even then, like, that is a very, very low peak-to-peak reading, and as we keep going down through the LLCs, I think at level 6 or 5, we'll actually see the peak-to-peak, like, not change significantly between, like, just running Y Cruncher versus moving the mouse around. So, yeah, not that that's particularly, like, the peak-to-peak measurement, again, it's not particularly useful, because it's the undershoot that ultimately crashes the CPU, so how much overshoot you have doesn't really matter. And it's also worth noting that as we go down on the LLC settings, technically it's not overshoot unless because the way load line calibration works is basically the VRM adjusts the output voltage to match the output current. So if the output current goes from, say, 200 amps to 20 amps, and your voltage goes up by proportionally to that change in output current, that's not overshoot. It's still in spec. It's only overshoot if, say, we're at level 8 LLC, and our target output voltage is 1.24 volts, and our maximum voltage is hitting like 1.28. Well, that's overshoot because we're 40 millivolts above the target voltage. It's not overshoot if you have, a operating voltage range of like 1.5 volts at 0 amps and then like 1.2 volts at 300 amps or something like that, which is what you would get with, I think, around the level 4 LLC. Anyway, let's go down to level 6. So level 7 is a significant improvement over level 8, but I wouldn't really say there's much reason to use level 7 because it's still not great. And this board does actually offer, like, the steps on the LLC are actually quite nice. I mean, I think I would kind of prefer if maybe 1, 2, and 3 weren't so crazy droopy, because they are basically useless as far as I'm concerned, but it's better to have more V-droop than not enough. Because there are some motherboards out there where no matter what you do, you get undershoot, and that's just kind of annoying. If you're doing like static CPU overclocks, because it just limits the kind of frequencies that you can achieve. Not necessarily a lot, depending on the board, but yeah, I do think it's best if a motherboard has the option that you can just have a... Well, it's sort of two things, because you do also have motherboards which have terrible voltage regulation, and even with heaps of V-droop, they still have terrible voltage regulation. So it's like you can't... Like, those you can't really fix, but... yeah, ideally you sort of want, you know... You want an LLC where you don't have any undershoot, and also it doesn't need to have heaps and heaps of V-droop. So, anyway, now we're at level 6 LLC with 1.38 volts set voltage. And we're going to go run Y-Cruncher again. And yeah, and now we're getting, like, the peak-to-peak values. Like, we're getting 60 millivolts peak-to-peak. Yeah. Also, why is our average? Oh, that's our current. There we go. There. I need to reset the statistics because the average voltage is like an average of all measurements, not an average of like right now. Anyway, so yeah, we're getting again around 1.318 volts. If I don't move the mouse, we're basically not getting undershoot, which is just awesome, right? Like that's really great. And if I do move the mouse, we get a bit more, you know, instead of being over 1.3 volts, we're now down to 1.29-ish, but honestly, this is insane voltage regulation performance. Like, peak to peak is at 70-something millivolts, even with me, you know, moving the mouse around. So honestly, level 6 LLC, like, if we were just... Like, we have to consider the fact that on the back of the CPU socket, we're probably seeing less undershoot than what the silicon is actually seeing. But level 6 is already very good. And I think if you are on a, you know, strong water cooling setup, and you don't want, like, you might actually be in a scenario where if you try to use something like level 5 or level 4, your idle voltage is going to end up being, like, sky high. So in that scenario, level 6 actually makes sense, because with level 6, you should still be within the range of having an idle voltage of somewhere around 1.4-ish, which is reasonable. So, yeah. Also, level 6 makes, like, perfect sense for... like benchmarking, potentially. Because if you're not intentionally flinging the mouse around, right, if you're just running Cinebench or something, that's going to be very easy for the VRM to deal with. So, yeah, like level 6 is already very impressive. Level 5 is actually quite droopy, so let's go to that next. And level 4... is very droopy. With level 4, we'll actually be above, like... Actually, I don't think we're going to be above 1.5 volts at idle, but the set voltage is going to be significantly above 1.5 volts. And the thing with that is, it's not really, like, I wouldn't really consider it like a degradation issue. Well, no, I think 1.5 at idle is probably not great. Anyway, let's just take a look at level 5 with 1.45. Where was I going with this? Oh, right. So the thing is, level 4, you might have noticed, is like what ASUS recommends for overclocking. And like the one issue you run into is, especially if you're on a 13900K and you have all the E-cores turned on and your hyperthreading turned on, at 100% load, the CPU pulls so much current that your like idle to full load voltage difference on level 4 LLC is absolutely insane. So that's one issue. that your idle voltage ends up really, really high if you're going to use level 4 LLC. But that's not, like 1.52 might be maybe okay-ish. I don't know. Like, I personally, I wouldn't feel comfortable with anything above like 1.45 at idle. Definitely wouldn't be comfortable with anything above 1.5. But anyway, the other issue is that I'm like, because I'm measuring from the back of the CPU socket, because if you look at level 5 LLC right now, right, this looks basically flawless. If I don't move the mouse, this actually looks the same as what we had on level 6 LLC, right, where the minimums are around 1.306 and our average voltage is 1.319. So this looks about the same as level 6. But if I start moving the mouse around, you'll notice we actually don't get undershoot. Like, there's no undershoot. So it makes me wonder if, like, ASUS recommends level 4 because when they were developing the motherboard, they actually checked the voltage regulation from the silicon side, right? Because we're checking it on the motherboard end. And so on the like CPU, there might still be undershoot that's just not picking up on the back of the CPU socket because of the impedance of the CPU socket. So that's sort of like my one thing I'm wondering about here is just like, okay, I can't measure level 4 actually being like better than level 5. Like level 5 is already like this already measures perfect. Like, there's no room for further improvement. The minimum voltage is basically the same as the average voltage, right? It's never actually going to be exactly the same because this is a CPU. This isn't like a resistor. Okay, this is still a CPU. This is a switching regulator. We're not measuring the voltage drop across a resistor connected to a battery. The voltage isn't going to be perfect. Like, it's not going to be exactly spot on. But this is like 14 millivolts. This is, and that's with me moving the mouse around. This is basically as good as it gets for voltage regulation on an LGA 1700 motherboard. So yeah, at level 5 LLC, it's already like, okay, like, it makes me think that probably there's like undershoot that we're not seeing on the back of the board. Because otherwise I don't know why ASUS would be recommending level 4 LLC. And yeah, so that's one thing I wanted to mention. Because yeah, the level 4 is very, very high V-droop. It's kind of a shame that like this board doesn't come with that feature that MSI has on their Z790 boards, which called like the load line saturation thing, which allows the motherboard. And I still don't get how that actually like works, because but on MSI boards, you can actually make the board sort of ignore the first however many amps of current. Like, you can specify this, so you can specify how much output current the VRM just ignores initially. So when you're at idle, your idle voltage can be reasonably low, and your idle voltage regulation isn't great, but it doesn't matter because you're at idle, right? Like, you're not going to blue screen at idle. If you undershoot at idle, it's not a big deal. If you have undershoot under high load, that's a problem. So on MSI boards, you can basically tell the VRM to like ignore 50 or 100 amps worth of V-droop, and you get a reasonable idle voltage. And then you can have like an insanely droopy LLC, and that just sort of deals with. Well, I haven't measured too many MSI boards, but the one that I did measure, like that one on just like raw voltage regulation doesn't compare to the Apex, like at all. You actually need to use a very high V-droop LLC on that board to get like a good voltage regulation. But anyway, so here's level 4. And yeah, level 4 looks Like now if I move the mouse, you can like really see the mouse input processing, right, is done as much lower amounts of power draw than Y-Cruncher is. So yeah, this is like within the measurement methodology that I've chosen here, this is the same as level 6. I mean level 5, right? So yeah. Now I'm not sure if this is actually like if maybe I measured closer to the silicon, maybe there would still be a difference. I don't know. I haven't measured. I'm not going to try to guess because this is not something I've really done like a bunch of testing on. I wish the CPU was BGA. That would make life so much easier. Because this isn't really like for GPUs. This actually isn't a concern. You don't have to worry about. Well, technically it is still like imperfect, but it's much less of a problem than an LGA socket. Because yeah, solder balls are significantly shorter than pins in sockets. Also, the way the pinout is set up for GPUs is better than how CPUs are done because of like packaging reasons. But anyway, yeah. So level 4 is like within is beyond if there's a benefit to using level 4, it is beyond my current measurement capabilities. So yeah, as in like the setup that I'm using here, not like we're not measuring current, we're measuring output voltage. So yeah. And the thing is though, if this board did have that functionality that MSI boards have where you can ignore some amount of output current, you could run level 4 LLC and just not worry about that. Which would be kind of neat. But anyway, so yeah, that's the LLC settings on the Apex. I would say like level 5 seems plenty good enough. Level 6, also very good. I'm kind of wondering maybe if they had shifted the levels so that there'd be like a level 5.5. Because there is quite a gap between 6 and 5, right? You have 1.38 versus 1.45 is to get the equivalent average voltage under load. So yeah, a level 5.5 would have maybe made sense, in which case they could have like shifted the other levels around because the board does have 8 levels of V-droop and you have like levels 1, 2, and 3, which we haven't even looked at because they're so high V-droop that they're impractical to test with a high like target voltage, right? Like the Dysense voltage that I'm currently aiming for. And this is one of the fun things about the Apex. Well, yeah, another fun thing about the Apex is this board actually gives you an average core voltage reading at the silicon of the CPU. And you don't have to like have any special software support for it because there technically like other boards can do this too, but it's not consistent. Here, the way ASUS has done it is very, very simple. They just have a little amplifier chip that replicates the core voltage from the Dysense circuitry, which is used by the Vcore VRM to monitor the voltage at the CPU. So they replicate the voltage from the Dysense circuitry, which is very accurate, over to the Super I/O. And the reason you don't connect the Dysense circuitry directly to the Super I/O is because the Super I/O is usually located in the middle of nowhere on the motherboard, and the Dysense circuitry is actually quite sensitive to interference. So you don't really want to be running it past, say, a VRM if possible. So yeah, you don't really want that circuitry like running all around the board. So you need an amplifier to replicate the voltage from the Dysense circuitry over to the Super I/O. That way the Dysense circuitry doesn't get affected by like external interference that it might pick up if you just routed it directly to the Super I/O, or if you connect a multimeter across it, that can cause havoc sometimes, because yeah, that circuitry is quite sensitive. But anyway, we do actually have a Dysense voltage reading directly from the Super I/O on this board. Yeah, so that's the Nuvoton chip over here. And anyway, if we hit Y cruncher, we should see that drop down to around 1.24-ish volts. Yeah, 1.234, right? And so that's like why on level 8 LLC we were using 1.24 volts is like, it actually works out to be roughly 1.2, it works out to be roughly the same here, right? And you can also see the whole like, where is this? Nope, there, right? Like our average voltage on the back of the socket right now is 1.32 volts, and on the actual CPU itself, it's like 1.234, and that's because the CPU socket has a bunch of resistance. So there's literally a 80 millivolt voltage drop across it. The one downside to the way that the ASUS DyeSense voltage is implemented here is that it's not, the Super I/O isn't necessarily super sensitive. So yeah, I think this one might be like some Super I/Os only have a resolution of like 12 millivolts. So they're not super precise. This actually looks like it might be 9, which is a bit of a weird number. I think I've seen one or like couple that are like 6 millivolts, but yeah, it's not super precise. It doesn't do millivolt level, accuracy. But it is better than having like normally the Vcore measurement that you get from the Super I/O on your typical motherboard is just whatever's on the back of the CPU socket. Which like you can work with that. It's just like you need to be aware of the limitations of that measurement, right? Like I'm hooking up the oscilloscope to the back of the CPU socket. So anyway, yeah, so that's the voltage regulation on the Maximus Z790 Apex. It's really, really good. There's exactly one other motherboard that's as good, and that's the Z690 Apex, which uses the exact same VRM, so that's not surprising, is it? Yeah, like, if you have an Apex, or like, yeah, actually, if you have a Z690 or a Z790 Apex, you can just use like level 5 LLC is probably sort of the most convenient option to go with, and then level 6 if you have like a lot of cooling. I would definitely not use 7 or 8. Like 8 has like scientific applications, right? Like you're testing a cooling system or something, you're going to use level 8 for that. But outside of that kind of application, level 8 doesn't make any sense because it's actually harmful to your like CPU stability. And level 7 is sort of in the same category for that. I'm not really sure. Like, I'm trying to think of a reason why you would actually want to use level 7. Like, this level 7 is a lot better than what some other boards have, where it's like level 8 and level 7 are like 10 millivolts apart. Here, there's a 70 millivolt gap. So I appreciate that. Actually, on that note, the load, like the difference between the different LLC settings on this board is really consistent. From 8 to 7, it's 70 millivolts. From 7 to 6, it's another 70 millivolts. From 6 to 5, it's another 70 millivolts. And then from 5 to 4, it's 75 millivolts. Which I think might actually just be a coincidence, but it is rather convenient. Because, yeah, there's some boards where it's like progressively gets bigger and bigger, the difference between the different LLC settings. And so, once you start getting towards the high V group end, you end up with settings that are like really far apart in terms of the effects that they have, which can be kind of annoying if you're trying to get something like if you're trying to find like a real sweet spot of a setting. So, yeah. Anyway, also you don't really, at least as far as I can tell, there's no point messing with any of the other VRM settings like switching frequency on this board because they don't really do anything, at least in my testing, if you're using a sensible LLC setting. I didn't bother to test them at level 8. I did try them at level 7, but at level 7, yeah, there wasn't really a measurable difference of any kind. So, yeah, that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, the usual YouTuber merch. There's a link to that down in the description. And I've also got a Bandcamp. There's a link to that in the description as well. And that's it for the video. So thank you for watching and goodbye.